Okay, so in multigrid, we take advantage of that. First, let's see why that is the case. We did two examples. In last lecture, we used the Lena picture, and after a few iterations, the solution is very, very smooth. It's basically like the smooth thing you can put in such a picture. And today, we also did a lot of iterations, and it turns out the solution area is like a smoothed version of the original analytical solution. So this is not an accident. This is because when I'm performing the Jacobi iterations, I'm splitting up the matrix D, the diagonal part, times UK plus 1 is equal to B minus L plus U times UK, right? And because the analytical solution D times U exact satisfies the same equation when you plug in U exact in both K and K plus 1th iteration. So if UK is already U exact, then UK plus 1 would also exactly be U exact. So if you subtract these two equations from each other, what you get is D times E to the K plus 1. If you define EK to be U exact minus UK, then D times EK plus 1 would be equal to minus of L plus U times EK. And EK plus 1 would be equal to minus of D inverse times L plus U times EK. And if we take this matrix to be R, then this whole thing would be equal to R to the K plus 1th power times E0, right? And the dominant eigenvector of the matrix R would determine what the error looked like after K iterations. So the eigenvectors of the matrix R depends on what D and L and U is. And depending on different operators, the matrix R would be different, and we need a different analysis. So today we are going to do an analysis of the Poisson's equation. All right, where in Poisson's equation, the R looks like that. So the R, when you put in, okay, so let's say D is equal to, let's say the 2D Poisson's equation, D is equal to minus 4 over delta x squared, etc., right? And L plus U would be 1 over delta x, 1 over delta x, 1 over delta x. It has this, it's the pentadiagonal matrix removing the diagonal part. It has still 1 over delta x's, delta x squares on 4 of the diagonals. So after the minus sign and the division, or the inverse, what we get is this 1 over delta x squares becomes 1/4. Diagonals are 0, and we get a quarters on 4 of the diagonals. And these 4 diagonal lines corresponds to the up neighbor, down neighbor, left neighbor, and right neighbor. Okay, so basically when you apply R to a grid, to a solution, or to an error field, it is making the average of the 4 neighbors, because it's basically taking 1 over 4 multiplied by the error at the 4 neighboring grid points and then add them together. It is taking the average. Alright? Because it is taking the average again and again, that is why it is becoming smoother and smoother. any extreme values is getting averaged out with its neighbors. All right. Okay, so it turns out that there are the eigenvectors are like that. So the eigenvectors, let's say Rx equal to lambda x. The x's, the xij's, are again like sinusoidal functions. They are sine of I times pi over n times sine of I of j times pi over n. This is multiplied by k1, this is multiplied by k2. And k1 and k2 corresponds to different integer values. Alright, and the lambdas would be a function of k1 and k2. Right, because once you plug in this into the averaging operator R, so this R is an averaging operator. I'm not going to go through the mathematics of deriving the lambda and x's, and you can go to Stellar, and there is in the reading section there is like pages of mathematics of actually deriving these, of verifying that this is the eigenvector and eigenvalues. Yes?
Just to clarify, so this is specific to the Poisson's?
This is specific to the Poisson's equation, yes. Okay, and there are two modes for which the lambda has the largest magnitude. Okay, the first mode, the first slowest mode, corresponds to the case that lambda is very approximate to 1. It is smaller than 1 but very close to 1. And this corresponds to the mode that k1 is equal to k2 equal to 1. This is the mode that is the smoothest. If you look at a two-dimensional domain and the contour is like that, that's almost exact the picture we saw last lecture, right? This is like the eigenvalue we saw in the error solution after 1,000 iterations last lecture. There is another slowest mode that corresponds to the case that lambda is approximately equal to -1. It's a little bit larger than -1, otherwise the solution is going to blow up. But it is very close to -1. This corresponds to the case that k1 is equal to k2 is equal to half of n. What is that mode? So, wait, is it half of n, or actually no? It goes all the way. It can goes all the way to n-1, right? n-1. So it's the largest, is the highest mode that this grid can sustain. So when k1, k2 are almost almost n, it's 1 below n. What happens is that xij has different signs. It's really a grid by grid oscillation. You can't even plot it. So if you look at one of the signs, it is basically sine of half pi, sine of 3 half pi, sine of 5 half pi. So it's basically minus plus 1 minus 1 plus 1 minus 1. If you plot it in one of the dimensions I, it is going from here to here to here, so it's like a mode that looks like that. In discrete Fourier transform, this is the highest mode, this grid, can sustain. This is the most oscillatory mode. And when you think of it, why does it have a slowly decaying mode? Because when you are taking the average between these two grids, what does it give us? It gives us this. The average of this gives us this. The average of this gives us this. So after one iteration, after one averaging, we get an oscillation that is almost completely flipped over. We get an oscillation that is like this. And this corresponds to lambda equal to -1, because after every iteration, the x gets flipped over while almost maintaining the same magnitude. Alright, so these are the two modes that are the slowest decaying mode. So a common question is, why don't we see this mode when we were doing the Jacobi iteration last lecture? The reason is, in the common picture, in almost all pictures, the original in the E0, so if you write down EK is equal to RK times E0, the component of this grid by grid oscillation in the original E0 or the original solution, original picture, is pretty small. That's what happens of typical pictures that like a human can look at. If you start with just a random noise, for example, you are going to see this mode after many iterations. Okay, any questions about this eigenvector analysis? So this is why the Jacobi iteration has a solution error that looks smooth after many iterations. And one particular thing that we want to take advantage is this exact feature, a multigrid. And we actually want to take advantage of this feature that the solution error, no matter what E0 is, the solution error is smooth. So this is okay multigrid, this is not okay. And we want to find ways to get rid of this slow mode. We want to find a way to make sure the solution error is going to be smooth, even if the solution error starts with something like that. So the technique we use to ensure that is called under relaxation. Okay.